Hey guys, Mr. Gordon here, talking to you about asteroids and dinosaurs. Why are we talking about asteroids and dinosaurs? Because it's a really good illustration of how the scientific process in the real world works, and we're basing it off of the story of a really big discovery that you guys have probably heard about, which is how did the dinosaurs end up extinct? So what I'm going to do is I'm going to guide you through this web page, which tells the story of how the discovery was made. The webpage is really cool, and I'll give you a link to it, but it's kind of long, and I didn't want to force you to read it, so I thought I would kind of narrate the way through it. So let's take a look at the story and what happened. So it says, asteroids and dinosaurs, unexpected twists, and an unfinished story, right? So it actually was a pretty interesting story of what happened. And it all started with this guy right here. His name is Walter Alvarez. And he was doing work right around the year 1980 that was not intended to try to figure out why the dinosaurs went extinct. He did not start off asking that question. He was doing something else entirely that led him to that. So just so you know, this website is reminding us that what we're going to see is the testing of a bunch of hypotheses. We're going to see multiple lines of evidence. We're going to see communicate in a diverse community. Sorry, I wrote over that there. That science is nonlinear. We've already heard that phrase. It's unpredictable and it's ongoing, and it often requires collaboration from those in many different disciplines. Disciplines in this case meaning different fields of study in science. So let's see where this story takes us. Okay, so here's Walter Alvarez again, and they're telling us what was he exactly doing at the time that he started making these interesting discoveries that led to him coming up with the idea that an asteroid killed the dinosaurs. So when Walter Alvarez was doing this work, the theory of plate tectonics was fairly new. So plate tectonics, you probably heard about it in middle school. It's a really big concept in earth science. It's one of the most important theories in earth science, and it says that the crust, the surface of the earth, is these plates that basically slowly move around the surface of the globe. And so it was a fairly new idea at the time. It had been sort of widely accepted about 10 years earlier. And one of the things that really helped cement this theory were these situations. So the coloring is the coloring that you see here is kind of fake, right? It's got stripes of light and dark brown, but what this actually is it's the magnetic field of the Earth flipping. And because that causes little crystals in rocks to flip in different directions, it actually makes it really easy for scientists to see the record of the magnetic pole flipping. And that, by seeing how that moves over time and how that's moved as rocks move, it helps provide really good evidence for plate tectonics. So what Walter Alvarez was doing was looking in some mountains in Italy and looking for evidence of this same thing, right? So it had been first discovered in the seafloor here, but he was looking for it in the mountains. And as he's doing that, he notices something strange. So he sees this specific boundary layer here. And you can see it's not big, right? This is a quarter. Right here, that's a quarter lying on this what's called boundary between two layers. So at this boundary, you've got one kind of rock over here and another kind of rock over here. And then the other thing that was really fascinating to him was that these ones over here, very few marine fossils. These ones over here, lots of marine fossils. So this very tiny boundary between one era in geology and another shows a huge difference in the amount of life that was there. So what is going on? What was going on that caused that? And that's kind of what started Walter Alvarez's journey, looking at what's called the KT boundary, the boundary between the Cretaceous and Tertiary periods. So let's look within the diagram of science of what he was doing. He made a surprising observation, right? Surprising observation that led him to ask new questions. Okay, so what did he do with this? So Conveniently, Walter Alvarez's father was Luis Alvarez, who was a Nobel Prize-winning physicist. And so Walter Alvarez goes to Luis Alvarez and said, how can I figure out what might have happened 65 million years ago that would have caused there to be a totally different set of fossils on either side? And so Luis Alvarez suggests that he look at something called beryllium-10, which is a radioactive isotope, and see if we can figure out how much would have passed, and then you can figure out whether this change in the rock layers was really quick or took a long time. Unfortunately, it turns out that the beryllium would just decay over that time. It wouldn't have lasted long enough. So they needed something new. They brought in a new person, and then they came up with this new idea, looking for iridium. So iridium is another element, and it's an element that's very rare naturally on Earth. So when we see iridium on Earth, it almost always has come from meteorites and meteorite dust. So then Walter and his dad come up with a couple ideas. So their idea is, well, okay, maybe the clay in this boundary was deposited quickly over a few years, or slowly over a few thousand years. So if it happened quickly, they expected they'd basically have no iridium in the layer, right? It would have happened so fast that there really wouldn't be enough meteorite action to lay some iridium down. Second possibility was maybe it happened slowly, and we would see we would see some amount, right? So they said 0.1 atoms per billion, not a lot, but more than 0. So what is Walter doing here? He is trying to share data and ideas so that he can generate a new hypothesis about how long it may have taken for this boundary to form. And then let's see what happens next. So he goes and does this iridium analysis using, and he has to actually go find more people. So these two people pictured here, Helen Michel and Frank Asaro, were two chemists that were brought in to help do this iridium analysis. And what did they find? Well, they had expected that if the clay took thousands of years to deposit, that they would see this level, 0.1 atoms per billion. Instead, they saw this level, 3 atoms per billion. 3 atoms per billion isn't a lot, but that is 30 times what they had expected. So there's something happened that caused this huge amount of iridium to be deposited. And what was going on? So that was confusing. And so then Walter Alvarez had to say, well, let me see, how else can I get some more information? So what he did was he actually went to existing research. So he went through published geological studies, and found a different place where that same rock boundary existed, and compared and looked for the iridium there too. And so again, this is what he found, right? The amount of iridium suddenly gets really high. Right here as the Cretaceous period ends, the amount of iridium suddenly gets really high. So what does that mean in terms of the process of science? So what Alvarez was doing was taking his results and realizing they were surprising, contradictory, and they required him to ask some new questions. He explored the literature. That means, what have other people said that helped him generate new hypotheses and see how his data might support a different hypothesis. Okay, so then what does he do? Well, he looks at existing ideas, and one of the big existing ideas about what might have happened when the Cretaceous era ended and the dinosaurs died out would have been a supernova. So a supernova is the most powerful force we know of in the universe. It's the explosive end of the life of a really big star. And so the thought might have been, maybe this was caused by a supernova. That's what triggered the dinosaurs' extinction. So here's your picture of a supernova, right? And a supernova would have given us the levels of iridium, these 3 atoms per billion, that he actually found. So that already is starting to say, okay, well, something is making some sense here. Let's see. But Alvarez also wanted to see, well, for sure, was this definitely a supernova, or could something else have been? Could something else explain this? So what does he do? He goes and looks for plutonium. So plutonium is extremely radioactive and also really rare, and that would have come here from a supernova. So he looks, was there plutonium in this same layer where there was the iridium? And they look, and what do they find? The actual observation was not what he was expected, right? This is one of those times when it sort of say, well, the scientist was wrong, and not wrong that he did something wrong, but wrong that he his existing expectation was overturned. He thought there would be plutonium, saying yes, there was a supernova, and actually he found none. Now what? Shoot. So let's see what this means in terms of science. He's asking questions. He's making new hypotheses about the iridium. He's thinking maybe it's supporting the hypothesis about the supernova, and then making another hypothesis about the plutonium, and suddenly finding this contradictory information that opposed the supernova hypothesis. Now what? Okay, so he goes back and he says, well, what do I actually know? What are my observations? So he takes the three main observations he's already made, which are the iridium, right? So he already found the iridium, knows that. The plutonium, no plutonium, so he knows that. And then this extinction, right? They know that the extinction occurred somewhere there. They don't know why, but it does. But all three pieces of that evidence seem to support a different hypothesis, which is an asteroid, right? An asteroid striking Earth at the end of the Cretaceous period. And so what he then started focusing on was, can a big asteroid impact explain these things that we would have seen at the end of the Cretaceous period? So what he does here is he gets inspired to think about a new idea and asks new questions, talks to other people about them, generates another hypothesis, sees if the data that he has match the hypothesis, and now he's supporting the hypothesis, right? In this case, the hypothesis about asteroids is being supported. Okay, so what happens next? Well, what happens next in 1980 is that Walter Alvarez and the people that he worked with published this paper right here. So this is a scientific paper. It's published in the journal Science, which is considered, sort of the most important of these scientific journals. So it means it's a really big deal. And this is where he lays out this hypothesis, right? So here it says this is published their hypothesis that linked the iridium to the dinosaur extinction, saying we saw this iridium in this layer where these two, where this extinction happened, and we think that it's linked. And so that sets off lots and lots of other work, because people want to know, can we confirm or not confirm what he's talking about? Can we find evidence supporting or evidence not supporting it? And then there's all these studies at these locations around the world. That's what this map is. So places in Canada, Denmark, Italy, Spain, even one in Colorado, where the other scientists have been looking for the same iridium detail. And so that happened, and then so we would consider this in science to be they published, they got feedback, they talked to other people, they came up with new ideas, right? Okay, so now it's really starting to get into be a controversy, because before Walter Alvarez came along, most scientists had thought that the extinction of the dinosaurs was gradual. So they started challenging him and saying, well, you need to be able to find these specific things that would have happened if there was some kind of asteroid impact, some kind of sudden event that happened. So they said, well, you should see extinctions, right? You would have seen lots and lots of extinctions of not just dinosaurs, but lots of things. You would have seen impact debris, right? You would have seen particles flying away all over the planet. You actually would have seen glass. This is kind of crazy, but the heat would have been so hot from this impact that it actually would have created little shards of glass from all of the silica in the Earth's crust that got superheated. So you would expect to find that. And then shock waves. You actually can see the impact of certain shock waves in rocks and minerals. And so the other scientists challenged and said, well, where are all of these other pieces of information? And it turned out they eventually were found, right? So the extinction, the impact debris, here's the glass, and this is what's called shocked quartz, which shows the evidence of the shock waves. So that's more, and here's some other things, tsunami debris. And then the final one was this really big one, the crater, right? So the crater. Well, if there was such a huge asteroid impact, there should be a crater from it. And that was a big question until this oil drilling company in 1991 found this pattern in the Yucatan Peninsula in Mexico and saw, hey, this is a crater. And after a little more investigation, it really turned out to be not just a crater, but a crater whose timing matches exactly what Alvarez was talking about. So here we're seeing more of his ideas, and all of these ideas being explored by lots of different scientists that eventually all do support the same controversy, or the same explanation. So really the evidence starts building and building towards this idea of the idea of the asteroid causing it, but it's not over, right? And we really can never truly say it's over. We can never say for sure there is absolute proof of this, because we don't say that in science. We're always open to new ideas, especially given new evidence. And there has been quite a lot of argument about whether other things could have happened, right? So here's Walter's idea, but other ideas include this massive volcanic activity in India that happened around the same time, huge climate change, or some other kind of tectonic action, like earthquakes or something that could have caused it to happen. And there's been argument after argument. There was recently another study that came out that pretty well backed up Walter Alvarez's initial idea, but still can be argument, especially if more evidence is found. So more and more evidence supports his hypothesis, but it still leads to more and more questions that lead to different hypotheses that get tested over time. So that's the basic story of Walter Alvarez and the KT boundary. So Walter Alvarez trying to understand this surprising finding he had about all of this, about the sudden lack of fossils in an area, leads him to this unexpected idea that one asteroid might have caused the dinosaur extinction. So that's the story, and I hope it's a really good illustration of the true process of science.